This is podcast 3.2 for chemistry, and we're going to talk about the rest of chapter 5. So we're going to do gas stoichiometry, we're going to talk about real versus ideal gases, Avogadro's law, and then Dalton's law of partial pressures. So the first thing that we haven't really covered yet, but we need to quickly review is STP. And STP stands for standard temperature and pressure. And standard pressure is 1 atmosphere. Standard temperature is 0 Kelvin, which would be 0 Celsius, which would be 273 Kelvin. And then really important relationship that you need to remember is that 1 mole of any gas at STP will have a volume of 22.4 liters. And that is the rule that Avogadro came up. So no matter what the gas, if it's at STP and you have a mole of it, it's going to have a volume of 22.4 liters. And that's important to us because we get to use it in some of our stoichiometry problems that we're going to be doing. So, rules for doing gas stoichiometry, everything is the same. You want to start with a balanced equation. You want to label what you know and you don't know. Here is the new part. We're going to be using the ideal gas law to solve for either volume or moles, and it just depends on the question what you're doing. And then we'll use dimensional analysis to determine our answer. And sometimes we do the dimensional analysis before PV equals nRT, so steps 3 and 4 are sometimes flipped. It just depends on the problem. But this is the new part that we're going to do, is using the ideal gas law. So our first problem here that we're going to try, oh my goodness, is solid potassium chlorate decomposes to produce solid potassium chloride and oxygen gas. What volume of oxygen gas measured at 40 degrees Celsius and 655 millimeters of mercury will be produced when 13.5 grams of potassium chlorate is decomposed? So our first step all the time is to make sure we have a balanced equation. So I'm going to write one. I have potassium chlorate, solid, decomposing into solid potassium chloride, and oxygen gas. So I have 3 and 2, which means I'm going to try and even these out like this. So there's my balanced equation. All right, let's write what I know and what I'm looking for. What volume of oxygen gas, so I'm looking for that, measured at, so I have a temperature of 40 and I have a pressure of 655 millimeters of mercury, will be produced when 13.5 grams of potassium chlorate is decomposed. Now when I'm doing this, I need to stop for a second and look, when am I going to be using PV equals nRT? And in order to do that, I'm going to be using PV equals nRT after I find my moles of oxygen, because I know that if I plug in moles of potassium chlorate, I'm going to get the volume of potassium chlorate out, which will not be the right answer. So when I'm doing this, I'm going to use PV equals nRT last, because I've got to do my stoichiometry first to go from the potassium chlorate to the oxygen gas. So I'm going to start with my 13.5 grams of potassium chlorate. And then the molar mass of potassium chlorate is 122.5, and that's 1 mole. And then for every 2 moles of potassium chlorate, we produce 3 moles of oxygen gas. And I had to do that so I could find my moles of oxygen gas and then plug into PV equals nRT to find my volume of oxygen gas. So if I do this, the answer comes out to be 0.165 moles of O2. So now I have my N, and I can use the ideal gas law to get into volume of oxygen gas. So PV equals nRT. The P I have, my pressure, I'm gonna, because the R I'm gonna use is in atmospheres, 0.0821, I'm gonna do some converting here really fast. So 655 millimeters of mercury, I would just divide that by 760 to get into atmospheres, and that's gonna be 0.862. And then we always want our temperature in Kelvin. So if I add 273 to that, I'm going to get 313. So doing that, then let's try again. My pressure is 0.862 atms. My volume, I don't know. The moles I just found. That's a 6. My R is my 0.0821. And then my temperature is 313. So if I do all that and I solve for V, I'm going to get 4.92 liters. And I should label that of oxygen so we know what we're talking about. So in this problem, we had to do stoichiometry first to find moles in order to plug that into PV equals nRT. All right, next question. When the following reaction occurs, how many grams of the P2O5 are produced when 82.54 milliliters of oxygen at 6,000 Kelvin and 45 atmospheres is completely consumed? Oh my goodness, those are really high pressure and a really high temperature. So, whoa, first thing we need to do here is balance that equation. I have 5 oxygens and 2 oxygens, which means I'm going to have to reverse those and put my 4 out there. All right, so there is my balanced equation. I'm going to rewrite it though here because I want to write what I know underneath and what I'm looking for. How many grams of the P2O5? So I'm looking for grams. Are produced when 82.54 milliliters of oxygen gas at, so there's my V. My pressure is 45 atmospheres. My temperature is 6,000 Kelvin. Okay, so in this one, I'm going to have to do PV equals nRT first, because what I'm going to solve for are my moles of oxygen, and then I can use stoichiometry to make my way to grams of the diphosphorus pentoxide. So the first thing I want to do is PV equals nRT. The pressure we're given is 45 atmospheres. The volume, and I want to put it in liters, would be 0.08254. I don't know N. My R is the same as last time, and my temperature is 6,000 Kelvin. So if I do this and I solve for N, I'm going to come up with 0.00754, and that's moles of oxygen. And then I can do my stoichiometry to get into grams of the P2O5. So I go right into the mole-to-mole ratio from the balanced equation because I'm already in moles. So for every 5 moles of oxygen gas that are put in, we get 2 moles of the diphosphorus pentoxide out. And then it wants grams of that, so 1 mole is 142 grams. And that is 0.428 grams of P2O5. So in that one, the roles were reversed. We did PV equals nRT first, and we did stoichiometry second. Okay, the next thing we're going to talk about is Dalton's law of partial pressures. So this is for mixtures of gases that we have in a container. P total, so total pressure in the container is equal to the sum of the individual pressures that you have of all the gases. So if you have a mixture of 10 gases, you're going to have to add up the individual pressures of all 10 gases. It is really important to note that the partial pressure is related to the moles of each gas. So I have a little example here. It says in the box, right here, there are 2 moles. So I have 2 moles of oxygen gas, and I have 1 mole of nitrogen gas. The total pressure in the box is 6 atmospheres. What are the partial pressures of nitrogen and oxygen gas? Those are related to the moles. So if I think I have 3 moles total of gas in my container, so if I'm looking for the nitrogen gas first, 1/3 of the moles is made up by nitrogen. So if 1/3 of the moles is nitrogen, that means 1/3 of the pressure is also nitrogen. So that would be 2 atms. And then 2/3 of the moles is oxygen, which means 2/3 of this would be 4 moles. So partial pressures are related to moles. There we go, are related to moles of gas. So you can see the relationship there in that example. I would write that one down in your handout because I'm pretty sure it's not there. All right, the other thing that goes along with Dalton's law of partial pressure is a lot of times we collect gases over water. That means that we have a setup that looks like this. We have our test tube here, and we have our potassium chlorate and our manganese dioxide in here. We heat the reaction to make it go faster, and what it does is it produces oxygen gas. We've stoppered the test tube and put a glass tubing that runs from there under the water, and we're going to collect it in this jar. When that happens, not only do we get the oxygen gas, but we also get some water vapor mixed in with that. And we need to take into account the water vapor when we're trying to figure out the pressure of the oxygen gas. It's important to subtract out the water vapor. We want just the dry gas value, and that means you have to get rid of water vapor when you're doing your calculations. So what that looks like is you would find your P total for your gas, and it's going to be the pressure of the gas minus the pressure of the water vapor. And this is found on a table. And you look it up by temperature. So you just look it up and you subtract it out from the pressure that you have. So here's our example with water vapor. We have when silicon dioxide reacts with carbon by heating, the following reaction occurs, and they give it to us. What would be the volume of carbon monoxide? So I'm looking for the volume of carbon monoxide collected over water that will be produced at 22. So let's see if I can squeeze all this stuff in. Temperature is 22 degrees Celsius. And pressure is equal to 657 millimeters of mercury. And this is when 96.25 grams of the silicon dioxide, so 96.25 grams, completely reacts. The vapor pressure of water at 22 degrees Celsius is 20 torr. What we're going to do with this information is adjust the pressure that they gave us. This is P total. We need to get the pressure of just the gas. So I'm going to get to that in a second, but the first thing I'm going to do is in this type of problem, we're going to have to do the stoichiometry first. Because we're looking for volume, we need to know moles of carbon monoxide, and in order to do that, we have to do the stoichiometry. So the first thing I'm going to do here is my stoichiometry, 96.25 grams of the silicon dioxide. Set up my table, and I'm going to go to grams first, and that molar mass is 60 is 1 mole. And then I can use my balanced equation that for every 1 mole of the silicon dioxide that goes in, we produce 2 moles of carbon monoxide. I'm going to stop there. Make sure you don't continue into grams of carbon monoxide because that's not what gets plugged into the PV equals nRT equation. The answer for this is 3.21 moles of silicon dioxide. So here we go with the other part, PV equals nRT. For the pressure then, if pressure total is 657, we need to subtract out the vapor pressure of water, which is 20 torr. And remember that torr and millimeters of mercury are the same, so I can just do the subtraction like that. which means that 637 torr is the pressure of just the gas. So this is just the gas. And I'm going to put that into atmospheres, so I'm just going to divide that by 760, and that's going to get me 0.838 atmospheres. So this is the pressure I'm going to plug in to PV equals nRT. So pressure is 0.838. The volume is what I'm looking for. The N is what I just solved for in stoichiometry. My R is still the same as it has been. And then the temperature I've got to remember to add 273. So I'm going to put 295 Kelvin in as my temperature. And when you solve for V, you end up with 92.8 liters of carbon monoxide. So the big thing here is when you're reading your problems, you need to make sure that it's saying over water, that you take into account the vapor pressure of water. All right, this is a bonus problem. It's not in your handout, and it doesn't really fit in with Dalton's law of partial pressures, but I wanted to squeeze this in here so that you guys can at least see it. The density of gases deals with rearranging PV equals nRT, and we need to remember density is mass over volume. So what we're going to do is we're going to rearrange this in order to find the density of a gas, and in this case we're finding dry air's density. At 15 degrees Celsius in 1 atmosphere, they're telling us its molar mass is 28.96 grams per mole. What you do with this is you take PV equals nRT, and we're going to try and solve for M over V, and you're going to look at this and say, well, there is no M, what do we do? You need to also remember that to find the moles of something, we take the mass divided by the molar mass. I'm going to take this formula and I'm going to plug that in for N. So instead of PV equals nRT, we have PV equals mRT over big M for molar mass. Now I have an M and a V that I can rearrange this equation and I can get a density. So density equals mass over volume. And if I rearrange this for M over V, what we end up with is pressure times molar mass over the gas constant times temperature. So this is what we're going to use to find the density of dry air. And then we just plug numbers in. So the pressure they gave us was 1 atmosphere. I'm going to use units here so we can make sure we end up with the correct units because it's not going to be grams per milliliter. Molar mass is 28.96 grams per mole. R is 0.0821 liter atmosphere mole Kelvin. And then our temperature that they gave us is 15 degrees Celsius, which would be 288 Kelvin. So really quickly, let's look at what cancels here. Kelvin, Kelvin, mole, mole, ATM, ATM. I'm left with grams per liter. So my units on this are going to be grams per liter. And when I take that and I plug it into the calculator, I get 1.22 grams per liter. That's the density of dry air. So make sure you're a little familiar with that you could rearrange PV equals nRT in order to find the density of a gas. Okay, back to the handout and the problems that are in there. So second problem with Dalton's law. We have a 5-liter container that contains nitrogen gas at 0.8 atmospheres and 0 degrees Celsius. That is 0 degrees Celsius. If the highest pressure the container can withstand before exploding is 3 atmospheres, what is the highest temperature to which the gas can be heated? Assume the volume is constant. What is the original temperature in Kelvin? So I have a container. Its volume is 5 liters. It is not 5 liters. That's a typo. That's supposed to be 0.5. That's what it says in your handout. So that should be 0.5 liters. And then they tell me the pressure is 0.8 ATMs. And the original temperature is 273 Kelvin because they told me it was 0 degrees Celsius. So let's see. If the highest pressure the container can withstand before exploding is 3 atmospheres, so volume was constant, that means it didn't change. And then what is the highest temperature? So these are all my 2's, my seconds, these are all my first conditions. Since volume is being held constant, I get to ignore it. It doesn't change. And then we have P1 over T1 equals P2 over T2. And then I just plug and chug. So P1 was my 0.8 ATMs. T1 is 273 Kelvin. My next pressure is 3 atmospheres. And I'm looking for the temperature that it can withstand. So solving for temperature, we would end up with 1024 Kelvin. So there you go. That's using the combined gas law. I don't think that's really a Dalton's law example, but that's more of a combined. Little bit out of order on that. So anyway, there you go. More example of what we talked about in the last podcast. All right, the last thing is real versus ideal gases. So no gas is ideal, but some are very close, and we assume that they are all ideal with the ones that we work with. Real gases have an attraction for each other, so they're not just hanging out in the container. They really do have an attraction. If I have a diatomic molecule here, there really is an attraction between them. And usually it's weak, but we call it LDF. Those are London dispersion forces. So it is an attraction between these molecules, and even though they're non-polar, like this could be a fluorine and a fluorine, a fluorine and a fluorine, there still is an attraction here, but we just assume there's not. So this one can be heading that direction and this one can be heading that direction, but there is a slight attraction between these two different molecules. Usually it's the really weak LDF forces. And these molecules really do take up space. They have volume, even though we assume that they don't individually. Gases are most ideal at low pressures, because a low pressure means they're very spaced out. They're not packed in close together. And then at really high temperatures. And high temperatures mean they're moving quickly, which gives them less time to interact with their neighbors as they fly by. So we want not a lot of gas molecules, and we want them moving really quickly. That limits the forces that they have on each other. We must correct ideal gas behavior when we're at high pressures and low temperatures, so the opposite of what I just said, because those attractive forces between the molecules become important and they can affect our calculations. So what we do is we use this really crazy looking formula here. It really is the ideal gas law. It's really, this is the P, and this is the V, and there's the nRT. We just have these corrected values, which you would find on a table if I go to the next slide. What you're going to see is there's a table here for A's and B's. So if I go back, you can just plug in for A and plug in for B, and N is moles. So we do all of this, and surprisingly, if you do that, your answer comes out awfully close to what you would have got had you just used PV equals nRT. So these adjustments that we make in this really crazy calculation, they don't give you much of a different answer. So really, this is just as good of an estimation of what you would get as opposed to this. So not something you have to memorize. These are values they would provide you, and they would also provide you with the formula. You would just have to plug in the numbers and solve for it. All right, that is the end of podcast 3.2. Big things are gas stoichiometry, making sure you can figure out the pathway that you follow to solve those, and also that you understand the difference between real and ideal gases.